Alright, so we'll be going through liquid chromatography, and we'll see. Inside there, we'll talk about thin layer stuff. This is just part one, alright? So this is just part one. Let us see how we can summarize these like types of chromatography. First, to start with, when we talk about liquid chromatography, so what do we mean when we say liquid chromatography? We just mean now when you say gas chromatography, just know that it's the gas that is the mobile phase. If it's liquid, then it is liquid which is in the mobile phase. The mobile phase is something that moves, that elute, and the process of moving is what we call elution. So, by definition, liquid chromatography is a technique, all right, where the mobile phase is the liquid. So we use the liquid as the mobile phase in this case, in which the ions will be helped to move and be separated, stuff like that. So to separate components in a mixture. So we'll be there to separate components in a mixture using this liquid mobile phase. So what we mean is this separation will be based on one is your analyte soluble in that mobile phase. Okay. If it is not soluble, then it means that it will move fast, you get. So, and also the interaction, okay, interaction with the stationary phase, how possible are they interact as this is moving? Let's say our mobile phase is moving within this column, because we know that the heart of the chromatograph is the column. So as the liquid is moving like that, which is our mobile phase, so those solute depends whether they are soluble in that liquid such that they can be able to live, or they are not. So this will matter. So if they are soluble, they will be able to move very fast with the liquid as it moves. But if they are insoluble, they won't move as the liquid, because this liquid, which is the mobile phase we have, is now moving fast, okay, or slowly, but it's moving. So as a result now, those solutes or analytes that you have will depend whether they will interact with this mobile phase or not. If they interact, then they will stay longer inside. If they don't interact, then they will come out. I mean, if they don't interact, it means um, they will remain coated, let's say, to the stationary phase. But the stationary phase will be something coated to this. If they don't, they are not soluble in this mobile phase. That means they won't be actually turned fast there to our detector. So the interaction will depends on the solubility and also the interaction of the stationary phase. So if it is stick to the stationary phase, it will take time to elute. If it doesn't stick, meaning that it interact more with the mobile phase which is moving, and that is our liquid, so it will be retained fast. So some compounds prefer to move, others prefer to stick, and that's how the separation will be done. So that is it about liquid chromatography. That is the working principle that is found here. So this is just a working principle. Let us see some types of chromatography. So the first type that we have is what we call paper chromatography. So under this, it works like this. Of course, it uses liquid, but the design is what we call paper chromatography, because we use the paper. I think this is the type of experiment we could do it in high schools, in secondary schools, all right? So you put the paper there, and the solute to move by capillary action, okay, because they are coming from high concentration, so they will move the moving of moisture through tin hole or tube or capillaries. So they will be moving like that as a result, because they are coming from high concentration, trying to dilute everything. So, and this is how it works. Sample is spotted on a paper. When the paper is placed in a solvent, which actually makes the solvent or the mobile phase to move by capillary action. This capillary action is what we call the movement of particles through a tin hole. All right. So once you dip this paper, so these guys which were in this solvent, they will start moving like that. They will start moving by capillary action, and they will be able to display themselves. So hence, the distance that has been traveled, we call it retention factor, how they are retained. So you can calculate this retention factor by saying the distance traveled by analyte over the distance of a solvent. So the solvent, the total distance of a solvent like this, it's here. The solvent moved to this, and these guys remain floating in this solvent with these initial distances, and we'll be able to tell. So once you find that retention factor, okay, if the retention factor is higher, so what will be the interpretation? If the retention factor, um, I said retention factor is the distance moved by solvent to the distance, I mean retention factor is the distance moved by analyte to the distance moved by the solvent, what you have put the whole lot of it. So the analyte are these particles. Then what you need to know is that some retention factor, okay, contains, like if we have same retention factor, we have same compound. For example, let's say we have a compound there and also they are of the same distance, so this might be the same compound, or of the same compound, these analytes. So if the spots are different, if retention factor are different, so that will mean impurity, like we saw here, we have different colors. Hence different compounds travel at a different distance, causing difference in retention time, how they are retained to the final point. In this case we use the eyes, but there's, like in high HPL, like high performance liquid chromatography, this is where we'll find we don't use, but we use detectors, specialized detectors, to know all these. So that is it about the the paper chromatography. This is just the type of chromatography we could use in high schools to determine the retention factor, or to separate these particles through using this paper called the paper chromatography. All right. So let's talk about thin layer chromatograph as well. So this thin layer chromatograph is the type of affinity chromatograph where we use a certain coat or a plate that has some absorbance or some special, let's say it has some special conductivity properties that will be used to actually absorb compound and move within it. It's a plate, by the way. So it is an affinity-based method used to separate non-volatile, those compounds that can't evaporate. We call them non-volatile at room temperature. So compound in a mixture, those ones that can't separate. So I repeat, this is an affinity-based method used to separate non-volatile compounds in a mixture, so those compounds that can't evaporate. So by that, even we assure that everything is closed, because we don't want something to evaporate. As a result, those things like the plates I'm talking about, sometimes they can be a glass, it can be a plastic or aluminium. So that aluminium, it will be coated with, it can be a silica gel or alumina or even cellulose, but the most one use is a thin layer called adsorbent. So adsorbent is the one we use, like we'll put there and dip there, deep inside there. So once we dip inside there, we dip this inside there, this plate or the glass or the plastic or the aluminium, which is coated. So the coat that you can use sometimes, most we use this adsorbent. So adsorbent is the one we most use. We can have silica gel, alumina, and cellulose, but as adsorbent property or material is the one which is coated to this paper, I mean plate or glass. So as a result, it will start absorbing, and these guys, they will be moving from here, they are moving up like that, and we'll be seeing particles separating like that. So they have moved from one place like that. So we have ensured that um, we have ensured that we have closed everything there like that, so that no vaporization is taking place. Okay, because vaporization will mean will bring something to disappear here if they can evaporate. So thin layer chromatography, the plates are usually like a variable, and with the standard uh, like particle size, like they will tell you to say the particle size that are needed in this, or it will come with those standard particle size. So that's how we this thin layer chromatography, I mean paper chromatograph or thin layer um, liquid chromatographs operate. So the standard parts are there to improve their reproducibility, because if you have the same standard, like things that are of the similar, you'll be there to reproduce the same result at different locations. So that is it. So the key feature that you need to understand is that this is very fast and it is very cheap, very sensitive, and it is used to identify compounds, to check the purity, and also to study biomolecule compounds such as carbohydrates, proteins, stuff like that. So that is it for silica, I mean for thin layer liquid chromatography. So special reagent are also used to enhance the identification, because if you can use special, I mean reagent there inside there, we add some special reagent. So that special reagent will help us to obtain this very fast and easily. So that will be the use of this guy. Okay. So this marks the end of thin layer liquid chromatography and also paper chromatography. So this marks the end. Thank you very much. Watch out for part 2, where we'll look at high performance liquid chromatography, which is the main needed type of liquid chromatography.